We are on part 2 of hypothesis testing and part 1 of our video on hypothesis testing. Sorry, still in my first cup of coffee. We did the statistical hypothesis, the null, and the alternative hypothesis. So we've done 3 out of the 6 steps that we need. If we take a look at it, remember that the null hypothesis, we refer to that as the HO, is always in equals, and this number is always in a population parameter. So we always have a mu for population and the population number. Then we have an alternative hypothesis, and we think that it's either going to be less than, greater than, or not equal to. These two numbers here, this number here, there we go. This number here and this number here will always be the same number, and it will always be a parameter, a population mean. Then the second thing that we did is we drew the curve and shaded. So if it's a less than, you go left, greater than, right, and two-tailed, both tails. Not equal to is both tails. Then you're going to choose a chart once we start learning different types from the chart. Remember, Z's are proportions and T's are means. So we're doing mean testing today, so we've been using a T distribution. You go to the chart and you look up the number that starts this critical value shading. That comes from an alpha level. The alpha level is given to you. Remember, if it's two-tailed, we divide. If you need to review that, go back and watch part 1 again. We can also use something called inverse T if you're using an 84, graphing calculator 84, and we also went over that. Now we're going to talk about the last 3 steps of hypothesis testing. First of all, we're going to talk about a test statistic, or it's also called a test value. So the number on the curve is a critical value. The number that you calculate is a test value. We're going to use a basic kind of z-score, but we use a t, x minus mu over the standard deviation, because usually we have a sample standard deviation, and then we're going to divide by the square root of the sample size. We divide by the square root of the sample size. If you notice, this comes from the confidence intervals, and this is your standard error from the confidence intervals. Confidence intervals and hypothesis tests sometimes have a lot in common, and we'll talk about that in a later section. So x minus mu, and then divided by the standard error. So we're going to take our sample mean minus the population mean. We're basically calculating kind of a z-score, but we call it a t now, because we're using a t-chart to look up these critical values, and we're using a sample standard deviation. That is why we use a t instead of a z. All right, and then we're going to talk about something whether we reject or fail. We're going to calculate this test value, and we're going to see if this value lands in shaded on the curve or white. Basically, we're just going to look at the curve, see where the shading starts. That's your critical value. If it lands in shaded or if it lands in white. We're going to reject if it lands in shaded, and we're going to fail to reject if it lands in the white, not shaded part. Then you're going to have a sentence that goes with this. If you reject, it's this sentence. We'll talk about it in a minute. And if you fail to reject, it's this sentence, and we'll go over our sentences as we go through. Okay, so first time going through, if you look at the part 1 that we did the other day, we practiced our HOs and HAs, our null and alternative, and we practiced the shading, and then we learned how to do the critical value. So if you need a refresher on that, go back and rewatch the part 1 video. Okay, so now we're going to do a whole problem. Okay, so our first step is always to set up a HO and a HA. All right, a researcher reports that the average salary of assistant professors is more than $42,000. A sample of 20 professors had a mean of $43,260. At an alpha 5, test the claim that professors earn more than $42,000. All right, so now you have a lot of numbers here. All right, so remember, we're doing a mean test. How do I know it's a mean? Because they're talking about the word average. So I do mu and mu. This is always in equals. This number is always the number that it is right now. It's before you go out and get your sample. It's based on the population now. This is a sample mean. See, this is the sample. That is not here. So it's 42,000. That's what it is now. And this researcher thinks that it's more than 42,000. So they're going to go out and get this sample of 20, do a greater than, and do more than 42,000. All right, so then we have our curve. This was step 2. It's a greater than. We put our 42,000 where it belongs. And then we shade right. Just pick a piece of the tail. This doesn't have to be accurate. This is for your visual reference. And now we're going to calculate something called a critical value here. The critical value comes from the t-chart. You need the degrees of freedom. So the sample size is 20. Degrees of freedom would be 19. And your alpha is 5%. You don't divide it because it is a one-tail. That is your shaded area. So your shaded area represents 5%. That is called an alpha level. All right, so we go to the t-chart and we go to 19. I need to clean this up. 19 and 5%, and we get 1.729. So the critical value is 1.729. If you want to do it on the calculator, you're going to go to second bars, inverse t, and you're going to do 0.05 because that was the alpha, and then the degrees of freedom is 19, enter, and then 1.729. It gave me the negative because remember it does the area to the left, so I'm kind of flipping the curve. If you want it to come out the right answer, then do 95. Go back. So I did this area, so it's giving me this area, which is symmetrical anyway. I'm just going to make a positive. If you want it to come out right, then you need to type into inverse t 95%. If you do not understand that, then just use the t-chart. It's just as easy. All right, now that is the steps that we did yesterday. So we're now going to calculate a t value, and this is going to be called a test value. Okay, the test value, or test statistic, it's also called, and I go back and forth between the two, is Tx, the sample mean minus the population mean, over what we call the standard error. The standard deviation of the sample, it's not a 5, sorry, over the square root of the sample size. The square root of the sample size shrinks your curve. Remember, the larger the sample, the smaller the variability is. All right, so the sample mean is 43,260 minus 42,000. The sample mean is 5230 divided by the sample size of 20. Okay, so let's talk about that. The sample mean from our sample standard deviation, the number of people we asked was 20, and then the 42,000. Okay, so if you're going to do this by hand, I would not. I would use this function on the calculator that I'm about to show you. So you're going to go to, remember, I told you that most of the semester is under stat tests, and you're going to go to t-test because that's what we're doing. We're running a t-test for means. So you're going to go to that t-test like we did t-intervals and confidence intervals. You're going to go to stats. The mean was, this is the HO. See the little O, H sub O, that's your HO, 42,000. The sample mean was 43,260. The sample standard deviation was 5230. The sample size, don't put degrees of freedom in here, 20. Okay, and this is the confusing part. You look at your HA. So this is mu is greater than, and then it goes up and gets that 42,000. That is the HO number, the null hypothesis number. So when the calculator reads it, it's going to be, this is your alternative. Mu is greater than 42,000. It goes up and gets it. So just look at your HA and follow the sign. This is a greater than test, so we're going to do the greater than one. Nope. That's the one we want. Okay, calculate. and we get a t of 1.077, and then this is going to be super important. It's called a p-value, and you'll learn this next week, but that p-value is super important, 1474. Okay, so let's write the t down first, 1.0, and we're just going to round it to the hundredths place, so 1.08. And we're going to just jot down that p-value for now, and we'll talk about it later. 0.1474. We usually take p-values to 4 places, and this is just like a z, so you want to round that to the hundredths. Okay, now this is called a test value. You're testing to see where your data lands. All right, so here's what this means in hypothesis testing. You have a null hypothesis set at 42,000. You're going to say that any number above that, right here, this line in the sand, right here, this 1.729, anything above that, we're going to say reject that null hypothesis. All right, so we're going to get 1.08, 1.08. That lands in white. See, the shaded starts at 1.729. That's why we call that a critical value. It lands in white, so we're just going to say the word. Since it lands in white, we're going to say fail to reject right now. All right, for just now. Why did we fail to reject? Well, we think that it's more than 42,000. Did our sample come out more than? Yeah. But was it that much more than? No, it wasn't this much bigger to say reject and say that we think that it's greater than. So what we're saying here is, did our sample come out more than 42,000? Yeah, sure it did. But was it a big enough difference that it landed out in this shaded? No. That's why we're going to fail to reject. So basically we're saying that maybe just due to sampling variability, we got a larger number, but it wasn't big enough to say that we think it's more than 42,000. In order to shift an entire curve away from a 42,000, centered at 42,000, you need to have a number that much larger in this area to reject this. All right, so we say fail to reject, and then if you go back up to the beginning page, just follow along your sentence, and it says fail to reject right here. There is no evidence to suggest that the true mean is not the 42,000. So we then write our answer right here. I'm going to make a text box, and I'll do it in red. Okay, so we say there is no evidence. I'm going to put that in. We don't have enough evidence to suggest that the mean salary of assistant professors is not 42,000. We have no evidence to shift this entire curve up. We were trying to shift an entire curve greater than 42,000. So what you're doing in a hypothesis test is you're trying to take an entire curve and, you're trying to take an entire curve of 42,000 and say the whole curve is greater than 42,000. So did we have enough evidence to do that, to shift it up? No. Why? Because our test value from our data landed in white. Okay. You probably cannot read that. See if I can change that back. There we go. So we have no evidence to suggest that the mean salary of assistant professors is 42,000. Okay, so when you're going through this, you always refer this back to the hoe. I know. So you either reject the hoe, I know, are you laughing? Or you fail to reject the hoe. You always look at your null hypothesis. Okay. Let's try another one. A national magazine claims that the average college student watches less than TV than the general public. The national average is 29.4 hours per week with a standard deviation of 2. And this includes like Netflix and stuff like that. So Ho is mu equals 29.2. That's the general public. 29.4. It's the general public. Okay, the national average is 29.4. And there's your standard deviation. A sample of 30 has a mean of 27. Oh, what am I doing? I'm thinking about something else. Sorry, guys. Okay, so we want it to be less than, a less than test. Sorry, I was thinking about something else. Okay, so we want it to be less than because we think college students watch less TV than the general public. Okay, remember these two numbers have to be the same and they have to both be a population. I was trying to do a calculation ahead of time in my head, so that's why I wrote 27 down. Anyway, okay, so we're set at 29.4. Is there enough evidence to support our claim that the college students watch less? Okay, so shade left because it's a less than. So step 1, this is our null. This is all alternative. This is what the population is. We think it's less. Put it there. Now we need to find a critical value. This will be step 3. Sample size is 30, so degrees of freedom is 29, and we have an alpha of 1%. Don't need to worry about divvying it up because, don't need to worry about dividing it up because it's all unshaded on this side. Okay, so we go to our t-distribution. I am going to clean this up. Okay. All right, so you're going to go to your t-distribution, and you're going to go down to 29. Because our sample size was 30. And then the alpha level on this was 1%. Alpha of 1%. So I go to 1%, and I go down, across, and I get 2462. And now I'm on the negative side, so I have to make it negative 2462. I will show you on the calculator. You can do second bars. Number 4, inverse t. This is for people that have this function. 0.01 and 29. And we get negative 2462. So same thing. These may be a little different because these are much more accurate, but either the chart is fine. So we're going to start shading right here. This is called, remember, our critical value. That's where the shading starts. I'm going to shade. So we're going to start shading at 2462. All right, now we need to go get our data and calculate a test value. Change my color. Okay, and it's going to be a t. So looking at the formula again, we get a sample mean. The sample from the college students was 27 minus the population over, and then this is the same thing from the confidence intervals, that's standard error. The standard deviation, it's the national average. They gave you a population standard deviation, which is even better, so we can just use that. And then the sample size was 30. All right, so we're going to put that in our calculator, and we're going to go through. We're going to do stat, test, t-test, and we type it in. The population was 29.4 hours. The sample for college students was 27. Standard deviation was 2. Sample size of 30. And this was a less than test. Look at your alternative hypothesis. You want to make it a less than. Just follow the sign from your from your alternative hypothesis. And then calculate. And we get, wow, negative 6.57. And this p-value, look and see that e to the negative 7? We're going to talk about that later, but that means it's 0.000000167. All right, so 6.57. So negative 6.57. And just jot this p-value down. We'll talk about it in our next lesson. It was 1.67 e to the negative 7. Okay, 1.67 e to the negative 7, which means it's 1, 2, 3, 4, 5, 6. So you move 7 places that way. So 6 zeros and then that. So that's your p-value, super small. Okay, so let's take a look at this. This negative 6.57, so the shading starts at negative 2.462. This is landing way, 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 like down here on, this is the curve. So if this is the curve, it's landing way, 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 way down here. So is the college students significantly less than the general population? Absolutely. Okay, so you're landing down here. The rest of the population is here. Is college students, 27, significantly lower than the population? Yes. Remember, this is like a Z, right? So when we learned a long time ago in Z scores with empirical rule, between negative 3 and 3 should be 99.7%. We're at negative 6.5. So if you're talking about it as a normal curve, you're like way down here. So is it significantly less? Yes. So does it definitely land in this critical region, it's called, or shaded area? Yes. So we're going to say reject. Okay, so we always reject the hoe. The hoe says it is 29.4. So we're going to say that there is strong evidence, because look how far down we are. There is strong evidence to suggest that college students do not watch 29.4 hours. Okay, let's make a little text box and type. Okay, and I'm going to say there is strong evidence. Why strong? Because we're landing so far down here. Evidence to suggest that the mean number of hours of TV for college students is not 9.4. And we landed in shaded, and there, if you go up to page 1, there is a sentence to follow. There is evidence to suggest that the true mean is not whatever. Okay, so in the hoe was 29.4. Just put it in context. Okay. All right, number 3. All right, why don't you take a minute, pause it, and see if you can go through and do it, and then start your video again. I'm going to go through and talk about it and do it, but see if you can try and do it on your own. Okay, the hoe is mu of 24,672, and your ha is different. It doesn't say, it says what they say it is now, and they want to see if it is different. Different means less than or greater than. So this is a less than or greater than. We're going to draw our curve. Oh, that was terrible. We're going to put 24,672 in, and then it is different, so we have to shade both the left and the right. Don't look at your sample data for this. Look in the words, your keywords. It different means we don't know if it's greater than or less. Okay, so degrees of freedom. Sample size is 28, so we're at 27, and your alpha is 0.01. Okay, now this is one of those ones where you have to divide up the alpha. This represents the total blue shaded, so you have to divide it into 2 because it's either a less than or greater than. So your alpha is going to be 0.005 on each end. That's what you're going to look up. So you either go to the T chart and go to 27 and 0.005 and get it. Okay, or you're going to go to second bars and go to inverse T, 0.005 and 27, and get it there. And you need both, so it's negative 2.77 and positive. See, it's 2771 on your chart. Okay, so we have both a 2.77, you can put 1, and negative 2.771 because it's a two-tailed test. Okay, so you shade both tails because it's a not equal, and you have to divvy up your alpha. Okay, now for the test value. Okay, T equals, we go get the sample mean of 25,226 minus 24,672. Sample standard deviation, or it wasn't the sample, it was the population, but that's okay. It's even better that we have one to use, and the square root of 28. A lot of people put 27 here. You only use the 27 for finding your critical value. Okay, now we go back to the calculator, and we put in stat, test, t-test, 24, that was me, 24, I think 672, I have to go back, 24,672, the sample mean was 25,226, and the standard deviation 3,251. 24,625, 3,251. Just making sure my stuff is okay. The sample size on this one was 28. 28, and here we go. And it was a not equal to. And if don't do that t thing by hand, use this function because you're going to need it for that p-value in the next lesson. Okay, our t was 0.91 and our p-value was 3752. So t is 0.91, 0.9, and then you can put 0.901 if you want, 0.902 if you want, but it's just 0.9, and our p-value is 3751. I'll need that p-value for our next lesson, so just jot it down. 3751, I think. Let me check. 52. All right. So now we're going to look and see where we land. This is 0.9, which is positive. The shading starts at there. We land in white. Was it bigger? Was it different? Yes, it was different. You're not always going to land dead on the population. Was it different? Yes. Was it bigger? Yes. But was it significantly bigger? No, because you landed in white. So this is a fail to reject. Okay, so we fail to reject the hoe, and we say text box. There is not enough evidence to suggest that the cost of rehab is other than or is not than hoe is 24,672 for stroke. I don't think these numbers are correct, but anyway. Okay, there is not enough evidence because we landed in white to suggest that the cost of rehab is not or other than the hoe. Okay. All right, last one of the day. A manufacturer of Duracell batteries claims that his batteries will have an average lifetime of 100. So why don't you try this one? Pause it, try it. So he's claiming that it's 100 for Duracell, and he's saying it's at least. Okay. The standard deviation is 20 hours. 90 batteries are selected, and their average lifetime was found to be 95. is the manufacturer correct at an alpha of 5%? Before you hit pause and try it, this is a tricky one. That's why I gave you this one. Okay. Duracell is saying that their batteries last at least 100 hours. So you think it's going to be a greater than. But if you're testing and a researcher testing against them, you're not going to agree with them. You're going to be like, hey, I really think that it lasts not 100 hours. They're saying at least. So you're going to say, be careful with this, less than. All right. Now here's why. Duracell says that they last at least. If you're a researcher that is going to test against what Duracell says, you're not going to do a hypothesis test that agrees with them. You're going to do a hypothesis test that's the opposite of them. So we're going to say less than. And I'll show you ways in case if you did a greater than to check yourself. Okay, so go ahead and pause and see if you can do the rest of the problem. So the Ho is 100. We're doing a less than test. The alpha is 0.05. You're going to go either to the calculator or your thing. The degrees of freedom on this one is we're at 90. So degrees of freedom is 90 minus 1, which is 89. You can go to the T-chart and you're going to go to 90 minus 81. It's kind of in between the two. It doesn't matter. So we go to 5%. And if you look at it, it's 1.66 either way. If you want to use your graphing calculator, you go to second, bars, inverse T, 0.05, and the degrees of freedom was 89, and they're giving us negative 1.662. So if you want to, on your chart, split the difference, you can. So if you have an 80 and 100, and then it's between 1.664 and 1.66, and your sample size is 90, you can say 1.662, which is actually the answer. But 1.66 is fine. Okay, so I'm going to make that critical value as negative 1.66 because we're on the negative side. All right, back to the test value. So the test value, remember this is called the critical value where the shading starts. This is the critical region where you're going to reject. Okay, so the test value, T is equal to, the sample mean was 95 minus 100. Standard deviation, 20. And the sample size is 90. Don't put 89 there. Okay, so we're going to go to our calculator, stat, test, t-test, and we go to, Duracell thinks it's 100. We got less than 95 with a standard deviation of 20. The sample size was 90, and we're going to do a less than test. Okay, so we get negative 2.37 and 0.0099. So we get negative 2.37 and 0.0099 is the p-value. Let's jot that down. Like I said, we'll talk about that in the next lesson. Okay, let's see where we land. Okay, we land in shaded. So we are going to reject. Okay, we reject the Ho. So we are going to say in our sentence, there is enough evidence to suggest that and sometimes we put true mean in, sometimes I forget to say true, but that the true mean lifetime of Duracell batteries is not 100 hours. What they're saying that it is, they're saying that it's 100, and we are rejecting that because we landed in shaded. So there is enough evidence to say the true mean lifetime is not 100. Okay, so let's say you did this problem and you did it wrong and you did it greater than because you read this word at least. Okay, so watch what happens. 2 ways to check yourself. All right, so let me do this in, what color haven't we used? Blue. So let's say that you did aha of mu greater than 100. So you got this, and you did 100 here, and you said greater than because they used the word at least. All right, so I'm showing a way for you to check yourself. Then you would have the exact same critical value at 1.66 just over here. All right, so then you go, that's going to be the same. It's just going to be on the other side. Then you go to the test value and you calculate it. You get a negative 2.37. So you are landing negative 2.37. You're landing over here. So one way to check yourself, if you do a hypothesis test and the shading is one side over here and you land over here, almost all the time you've done something wrong. Okay. If you're doing a one-tailed test and your shading's here, you should be landing on this side to compare. If you shade right and land left on the other side of the mean, this is probably wrong. Another way to catch yourself in a mistake on a less than greater than, this is only for less than greater than. If it's two-tailed, then you're shaded both sides and you can't use that. Okay, now watch. If you go to stat tests and you made a mistake, this is all the same. 100's the same, 20's the same, 90's the same, everything's the same. If you make a mistake and on a one-tailed test and say it's greater than instead of less than, okay, because that's the only thing that's going to change is what side you shaded, and you hit calculate, here's another way you can catch yourself. If this number right here, this p-value number, which you don't know what it is yet, the test value is still negative 2.37. That has nothing to do with the greater than or less than. This is where your data lands, either on the left side or the right side. If you get there, okay, if you get there and you land on the wrong side, it's going to give you a p-value over 50%. See how it's 99%? Okay, so if your p-value comes out to be over 50%, look, see how this one's less than 1% and this is almost 100%. If that happens, then you've made a mistake on the less than greater than. All right, so this is wrong. But there's 2 ways then to catch yourself. If you shade on one and land on the other, you've done it wrong. And then almost always. And then if this p-value, which you don't know what it is yet, if it's greater than 50 on a one-tail test, that you've probably done it wrong. And you need to go back in and toggle from like a greater than to less than. Okay, that is our first lesson in hypothesis testing.